Hi, my name is Alex Reneau. I'm an undergraduate student at Northwestern University's Computer Science Department, and the second author on this paper is Jason Wilson, an assistant professor at Franklin and Marshall College's Computer Science Department. Today I will be presenting our paper, Supporting User Autonomy with Multimodal Fusion to Detect when a User Needs Assistance from a Social Robot. So a common problem with older adults is that they have to manage multiple different medications. One notable strategy to solve this problem is pill organizers. However, for older adults, this task of pill sorting can be non-trivial because of reduced executive functioning. This leads older adults to require a greater need of assistance. Still, it's important to note that with this opportunity to provide help, there's also room to inflict harm. With reduced executive functioning, older adults might find themselves in more vulnerable positions that might be easily taken advantage of. Or you might describe this as posing a threat to the user's autonomy. It can be difficult for an assistive robot to maintain the autonomy of the user at times because it might try to over-assist the user, overpowering their preferences and possibly forcing them in a direction they don't wish to take. So our work primarily focuses on enabling a robot to provide valuable assistance while supporting their autonomy. So what does supporting the user's autonomy actually look like? Well, for one, we need to provide help when the user actually needs help. And if they don't need help, our assistive robot might provide encouragement or completely disengage until needed. And this requires that our robot accurately predicts when the user needs help. So with better performance, we'll be more confidently assisting and supporting the user's autonomy. So to quickly go over the original experiment that played a role in motivating the work for this paper, it was in our original experiment that the robot was present. It assisted 19 people in a medication sorting task, and for every single user interaction, we recorded audio and video capturing gaze direction, user speech, user gestures, robot speech, and task events. So the ground truth values for this video, for this experiment, were tracked for each video. They were determined by the majority vote of 3 human annotators, which is basically just they need help or they don't need help. And finally, a significant piece of the original work was the development of 4 independent models using the collected and annotated data. So this brings us to the independent models, which were our first attempt to develop models to automatically enable the robot to help the user. So first we have the eye gaze models, which is the mutual gaze and the confirmatory gaze models. These models come from previous work and have been shown in the literature, where the mutual gaze model just tracks if the person gazes at the task, then at the robot, then back at the task to infer if they need help. And the confirmatory gaze model is just the inverse of that, where it tracks if the person gazes at the robot, then at the task, then back at the robot. And then we have a task model, which has not been shown in the literature until this work, which just uses the change in the number of steps left to complete the task to indicate if the user needs help. So if the user takes a step closer to the goal state, it's unlikely they need help. If they take a step away from the goal state or make no progress, it's likely they need help. And then finally, we have a lexical model, which just uses simple keyword spotting to indicate if the user needs help, which is, for example, I need help. That means the user needs help. So what was the impact of these models? How well did they perform? So to start, these are all high precision, low recall models, which we can see down below in this figure. And also, our task model is notably the best performing independent model with an F1 score of 0.51, which is also visible in the figure down below. And lastly, we note that these results are decent, but not near as close as we want them to be. So therefore, we believe that combining the independent models would raise recall and increase performance, giving us a better overall model. So this brings us to our hypotheses, where an important point to highlight is that when we provide a better model, we are likely to increase the robot's ability to provide timely assistance to the user. So how do we build a better model? Well, we had two hypotheses, one being that combining our 4 high-precision low recall models together using decision level or late fusion would increase performance and give us a better model. And then two, capturing the temporal dependencies with a sliding window method would increase performance and give us a better model. So now kind of moving into the fusion pipeline a little bit. On the left side, we see this blue box called annotated data, which here is just where the hand annotated data that was collected from user studies, which is the gaze direction, user speech, and task events. And then in the middle, we have these red boxes, the confirmatory gaze model, the task model, mutual gaze, and lexical models. And then we have a green box where we train the machine learning algorithm for fusion. And then finally, this last box on the right is our decision result. So the annotated data from the collected user studies are fed in as inputs to the 4 independent models, and then a continuous value is outputted from each of the 4 independent models. Abstractly, the value represents the model's predictions of whether the person needs help at that moment. We represent this as a continuous value from 0 to 1, where 0 means they do not need help and 1 means they do need help. The outputs from the independent models are packaged into a feature vector that is then passed in as an input into the fusion model, where the fusion model then just outputs a Boolean value. They need help or they don't need help. So here we'll explain the role of the sliding window method and how it works. The sliding window method captures temporal dependencies by including previous events in the current decision. So what's an event? An event is a feature vector that contains outputs of the independent models. And moving forward, the amount of previous feature vectors or events that we include is determined by the window size parameter S, which we can see down below in the notation. In the case that the window size is 1, this means that there is no sliding window method. Or in other words, we're not including history at all. It's just the current feature vector. So as we start to increase S, we begin to utilize more previous feature vectors or events. And our final feature vector, x hat t, will have a total of S windows because t is 1 plus S minus 1 events. And then it will also include the previous S minus 1 events. And finally, we have an edge case that if there isn't enough previous feature vectors available to us, we just end up filling in the rest of the window with 0 vectors. So to start off, we're going to focus on the meat of this loop. So it's the meat of our experimental setup, and we do these 3 steps for every experiment. First, we build the windowed feature vectors using the feature vectors containing the outputs of the independent models to capture temporal dependencies. Then we randomly shuffle the windowed feature vectors to even out our data distribution. And then we run a 10-fold cross-validation using our randomly shuffled windowed feature vectors. For each fold of cross-validation, we balance a training set, which is just evening out the true and false data points in the training set. So we run this process for each of the machine learning algorithms, SVM, logistic regression, decision tree, naive Bayes, and random forest. And we chose these algorithms because they work well with small amounts of data and have fast training times. On top of that, we run each algorithm and the 3-step process for each window size 1 through 50. And then finally, on top of that, we run each algorithm and the 3-step process for each window sizes 1 through 50 another 50 times for a level of confidence in our results. And in total, we ran 12,500 experiments, accounting for the 50 iterations, 50 window sizes, and 5 algorithms. Lastly, to measure out results of these experiments, we looked at the F1 scores and calculated the receiver operating characteristic and precision recall curves. So now moving on to the results of our experiments, we found that Fusion does better than the independent models, where the best performing independent model had an F1 score of 0.51 and the worst performing Fusion model had an F1 score of 0.62, showing significance. And we also discovered that the sliding window method successfully captures temporal dependencies. And we also found that the greatest change in performance was typically in the smaller window sizes, and that the best performing model window size pair was the random forest with a window size of 47. So the purpose of this figure is just to kind of highlight the sliding window method and how it captures temporal dependencies and its effect on performance behavior. So to kind of explain the figure itself, it's made with 50 windows. For each window, the corresponding F1 score is the weighted average of 50 F1 scores just to reduce variability. We're going to focus on the all models curve, which represents the average of all the algorithms for each window. So just focusing on the window size here, we can see an early growth from window size 1 through 10. And then later on, we can see kind of it to begin to plateau a little bit. Generally, we saw it starting to plateau around window size 30 and even more so around window size 50. And then after that, there's no significant results. And then otherwise, we note that the random forest model is very noticeably outperforming the other models, which we can continue to see in the next couple of slides. So we basically just use this figure, this box plot, to pull out the best model window size pairs. So this box plot was constructed such that for each window, the corresponding F1 score is the weighted average of 50 F1 scores, just to reduce variability once again from randomization. And then the orange line inside of each of the boxes is the median F1 score for the model. And the bottom of the box marks the first quartile of the F1 score distribution for the model, and the top of the box marks the third quartile. The head and the tails mark the max and min values. So this plot confirms our hypothesis that Fusion is better, generally just because even at the window size of 1, all the models way outperform the best independent model performance with an F-score of 0.51. And the best performing model window size pair is the random forest model at window size 47. It is also generally better than all the other models regardless of the window size. And then also we can see that the decision tree model performs second best, and like the random forest model, it performs optimally at window size 47, showing a correlation between the two. And this hints that these tree algorithms are better, which brings us to our next slide. So the purpose of this table here is just to focus on the models rather than the window size and show that the tree models outperform the non-tree models. So to explain the table a little bit, here we're just varying the window size parameter using window sizes 1 through 50 and plot the true positive versus false positive rates to get the receiver operating characteristic as an additional measure. On top of this, to see how the models compare, we also plot the precision recall for each of the window sizes 1 through 50. We calculate the area under the curve score for these curves to give us numbers for comparison. The area under the curve is a measure of how well a given model performs under a variety of parameters. The greater the area under the curve for a model, the better it is generally performing. So the random forest model is by far best performing overall model, as we can see here in the table. And our second best overall model is the decision tree, as we can see here in the table as well. This shows that even the worst performing tree model, which is the decision tree model, performs better overall compared to the best area under the curve scores for all of the other non-tree models, concluding that the tree models outperform the non-tree models. So finally, we can confidently say that Fusion is a great improvement of the independent models, and even our worst Fusion model strongly outperformed the best independent model. Then we can also assert that the sliding window method effectively captures temporal dependencies, leading to better performance, which concludes both of our hypotheses. So we hope that our work will contribute to helping the robot give more timely assistance to the user while maintaining and supporting their autonomy. But this brings into light some details for future work. The first and most important being that we still need to test our findings in a real setting. And also that we're working within a very specific task domain, so we're looking to expand our work to other task domains and add more modalities for generalizability purposes. And lastly, we are lacking ways to collect user feedback during and after the human-robot interaction, which we'll need because we want to employ an adaptive learning approach to keep improving our model. So we're looking to develop methods to collect user feedback because of that. And that's it. Thank you very much for your time.